Hello, my name is Stanislaw and I'm excited to share the results of my projects focused on enabling the execution of WASI applications on an internet computer. To understand this achievement, let me first explain the main terms involved. As you may know, the canisters running on the internet computer are powered by WebAssembly. The WebAssembly, or Wasm, is a portable instruction set that is compatible with various execution platforms. It is modular, safe, performant, and can be run within web browsers. A standalone Wasm binary operates within a sandbox environment. It can make changes to its memory, but it cannot access any operating system resources like time, randomness, internet access, the file system, or the console. To address this limitation, the WebAssembly binary has to explicitly import the required functionality. The execution environment then binds the necessary imports with the corresponding implementations. For instance, if a WebAssembly binary needs to output something into the console of your browser, it inputs a JavaScript function from outside the sandbox that would then output the text to the console. You might wonder how an execution environment would know which functions it needs to provide. This is where WebAssembly System Interface comes into play. It defines a sufficient set of functions to represent an abstract operating system. This way, any application compiled for WASI can be executed in any Wasm runtime environment that supports the interface. Nowadays, WASI is gaining traction as a common target for various languages and products, likely becoming the primary target for WebAssembly programs in the future. WASI now allows executing interpreters like JavaScript, Python, Ruby, and Go within the Wasm runtime environment. The compiled languages like Swift, C++, C#, and of course Rust do support the WASI as a compilation target. Hence, supporting WASI on the internet computer would greatly expand its ecosystem. At the moment, Internet Computer does not offer WASI functions for import. The canister with WASI dependencies cannot be deployed as a result, but we can try to manually remove the dependencies and make the canister deployable after all. This process looks as follows. First, we create a binary that contains some WASI imports. We make sure that during compilation the polyfill implementation is also present in the binary. Then, all of the WASI calls are rewired to call the corresponding polyfill implementations instead. Finally, the WASI imports can be completely removed and we have the binary that can be deployed. To facilitate this process, I have developed 3 projects: WASI to IC, a conversion tool that swaps the import dependencies of a WASI binary; IC WASI polyfill, a library containing the WASI polyfill implementations; and finally StableFS, a file system implementation based on the IC stable structures. It serves as a backend for the polyfill library calls. Now, if you have some Rust project that compiles to a WASI, you can simply add the dependencies to the polyfill library and after Wasm file is produced, use the WASI to IC command to redirect all the WASI calls and clean out any WASI imports. As a result, you should have a canister that can be deployed and run inside the IC environment. For detailed examples and demonstrations, visit the GitHub page www.github.com/Wasm-Forge. Explore the demos showcasing a basic Hello World application running the SQLite engine or executing the Bohr JavaScript interpreter directly inside your canister. Thank you for your attention and feel free to explore the examples and share your feedback.